All right. So we're going to re-look at this question that we just did on the whiteboards and talk about how to formalize it, how to model it using the 4 different ways. You on the whiteboard have been able to model it using logic, which is brilliant. And I'm going to take your logic and show how that logic matches the tables, matches the words, matches the graphs, matches the equation. Okay? So we're going to redo this question a whole bunch of different ways so we can see why that logic works and how we can use that logic to answer other questions. So it's the same scenario. Christmas Eve started snowing at a rate of 2 centimeters per hour. After 7 hours of steady snowfall, there was 22 centimeters of snow on the ground. So first, what's the independent variable? What is the thing that goes along the bottom in this scenario? Time. And time is in what scale? Good. And therefore, what's the dependent variable? Good. And in what variable or units is in centimeters? Because the amount of snow depends on how much time has passed. What's different in this question is we don't have enough information to get this entire table. In all the questions we've been doing before, we would have had the initial value and the rate of change, and we could fill out the table. Here, all we have is one bit of information. Somewhere in the future, if you counted right now as the beginning, in the future, we know there is 7 hours later, there is 22 centimeters of snow. We know that bit of information. So we can throw that in the table. We can also graph that bit of information. So let's go to 7. And be careful of your scale here. You see how every 2 squares is equal to 1 hour. And every square here is worth 2. So it goes 2, 4, 6, 8, 10, 12. So be careful of your scale when you're graphing this. But we know one bit of information. We know that at 7 hours, all the way down here, we've got 22 centimeters of snow. So that's going to be right in between the 20 and the 24. That right there is a coordinate. It's this coordinate right here. 722. We know that bit of value, that information. There's one other bit of information we know. We know at 7 hours is 22, but we know something else. Is that true? I think there was some snow at the beginning of our time, okay? Which is what the question asked us. We have to figure out how much snow was at the beginning, okay? This is a partial variation, not a direct variation. Does that make sense? Good. What other information do I know? Yes, it goes up 2 centimeters per hour. That is the rate of change. That is our slope. So if I have 1 point on here and I know the slope, I can get another point. Let's do a slope of 2. A slope of 2 means rise 2, run 1. So from here, I want you to rise 2 and run 1. Now, be careful of your scale. If you rise 2 centimeters, how many squares is that on your scale?
No, that's 1.
That's right. So you're only going to rise 1 square because that's 2 centimeters. And then I need to run 1. How many squares is 1 hour? 2 squares. Yeah, 2 squares is 1. Yeah, it feels a little backwards. To help, let's think about what the table would tell us. If it goes up by 2 every hour, how much snow is there at 8 hours? 24. Did we put our point in the right spot at 24? I think we did. 8 hours and 24. Now I have 2 points. Is this enough to draw my line? If I've got 2 points, can I draw my line? Yeah. Remember, I only need 2 points to do this. But here's the catch. It's a little bit hard to draw a line accurately with only 2 points. So let's get a couple of more points to help with that. We can go backwards. Most of the time we think about going forwards, going up by 2, up by 2, up by 2. Well, this goes up by 2, except we're at the 7-hour mark. Can we go backwards? Where were we an hour ago? At 20, that's right. And how about the hour before that? Before that? Does 8 sound familiar? Does 8 sound familiar? That was the answer that we got when we did it on the whiteboard. We just went back, all the way back to the 0 moment, when time was 0, the initial value before it started snowing. We're able to figure out the 8. Now you did this more efficiently up at the whiteboards. You didn't make a table and just start counting backwards. You said, you know what? It goes 2 centimeters an hour, and you have to go back 7 hours. So you jumped from here to there by saying 12 minus 14, right? 2 an hour times 7 hours is 14. So you jumped from here straight back to the 0, which was way more efficiently than the table. And I'm glad you did that, because the table is not an efficient way to do this. But by using the table, we can get a whole bunch of other points on this graph to make it more of a more accurate model. So let's go backwards. 6 hours, there's 20. 5 hours, there's 18. 4, there's 16. Keep plotting those points going backwards. And look what happens when you go backwards. You end up at 8. And that is, what do we call that thing where the line crosses this axis? The y-intercept, the b value. You can even use your slope triangle to help you go backwards if you needed. Just keep going backwards. And we get to this point here, which is the y-intercept, the flat rate, the b, the initial value, how much snow was on the ground before we started keeping track, before the time started, before it started snowing. So can I now model this whole situation with an equation? The question told me the slope. We just worked backwards on the graph and in the table to get our y-intercept. So put those 2 bits of information together and give me an equation. Very nice. So the questions that we're doing here are finding equations using 2 new new bits of information. Well, not new, but different information. In the test you just wrote, you were finding the equation given the slope and the y-intercept. In this question, we are given a slope and some other point that's not the y-intercept. But we could use our logic, we could use tables, we could use graphs to figure out the y-intercept to come up with the equation. Questions so far? So we were able to do it with a table. We were able to do it on the whiteboards. We're using logic. You were able to do it on a graph. Now let's do it algebraically. So again, on the bottom of your worksheet, we're still doing the same question, except now we're going to do it algebraically. So again, what is the rate of change or the slope in this scenario? We already identified this. Well, what's the slope? 2. So m equals 2. Write an ordered pair that belongs to this relationship. So tell me a point that they're giving us. They're not giving us the y-intercept, but they are giving us a bit of information. 722. Very good. That comes straight from the information here. By the way, notice that the coordinate is time. And I'm going to call this money, even though it's not money. Well, no, I'll call it centimeters now. I'll call it money later. Time and a distance is a common coordinate. Time, remember I said almost always is the independent variable, and then what you're measuring becomes the second number. So time comes first. The thing you're measuring, whether it's distance, in a second we're going to measure money, comes second. Now, how much snow was there before it started snowing? This is working backwards to do our initial value. Again, I already know that you know how to do it logically. I know you know how to do it using the graph and the table. We're now going to do it graphically or algebraically. So we know so far that the equation is y equals 2x plus something. We're going to pretend we don't know what the initial value is, even though we've solved it twice. We don't know what the initial value is. So I can write the equation so far with y equals m, which is 2, x plus b, which I don't know. How am I going to figure it out? Just like you did, I'm figuring it out by using the coordinate. We're going to take this coordinate and sub it in. Sub it in means substitute it in. Put those values for x and y into the equation. Which of those letters or those numbers is the x, the 7 or the 22? Right. Remember, it goes x, then y. Right? Your x comes first algebraically, so it comes first, or alphabetically, so it comes first algebraically. So wherever I see an x, I'm going to replace it with 7. And wherever I see a y, I'm going to replace it with what number? 22. And now the math you're going to do is mimic the logic you just did. And it matches all the algebra rules that we've been doing. What's the first operation I got to do? Sorry? 2 times 7. We got to do multiplying. So 2 times 7, help me out, is 14. And my whole goal is to figure out the b value. If my goal is to figure out the b value, I have to get rid of this 14. How do I get rid of it? Right? Inverse operation, subtract 14. (22 minus 14 is 8. And I can't stress enough how this math here matches exactly this math you did on the whiteboards. I saw your first step, everyone did 2 times 7, got 14. And then what was your next step? 22 minus 14 is there. All the algebra is doing is formalizing the logic that you already have. Okay? So now I got my M from the question. I did some algebra to get the B. So therefore, what's the equation? Y equals 8. Starting with 8 centimeters of snow, and for every X, for every hour, you get 2 more centimeters of snow. Okay? So we've like overkilled that question, but I wanted to make the connection between the logic that you already know how to do to the graph, to the table, and to the equation. Let's look at a new scenario. And when I say new, you almost roll your eyes because what am I talking about again? The fair question all the time. Okay? At the fair, it costs $4 per ride plus an entrance fee. Ashton went on 5 rides and spent a total of $32 at the fair. What was the entrance fee? So, for starters, if Ashton went on 32 rides, 5 rides, and it costs 32, do I just divide that?
No, because you have to figure out the entrance fee.
Yes, very good. Okay, the most common mistake I see is people say, oh, it's five rides, you spend 32, you got to go off and divide that. You don't, because we have to know about the entrance fee. Okay, so we're going to try and do this all algebraically. What is the rate of change? The rise and the run. What's the slope? What's the rate of change? What thing changes all the time? Yes. Right? It's $4 per ride. So you either pay $4 or $8 or $12, or that's the thing that changes. Okay, good. What's a point? What information do I have? Yes, 5 and 32. This is time, money. You're going to hear me say time and money all the time because money depends on how much time you're there, how many rides you go on. It's not really like you're not measuring time with rides, but you kind of are, right? You're saying how every time you go on a ride, it's like every minute or every hour. You know, it happens all the time. Okay. What's missing is my equation. Give me the equation so far. I know parts of the equation. It's y equals mx plus b. This one I already know is y equals 4x plus b. How do I get the b value? 4 times 5, then subtracted from 32. Okay, that's the logic. What's the algebra? I'm taking this point, substituting it in. So it's 4 times 5. And the answer is 32. Help me out here. 4 times 5 is 20. How do I get b minus by itself? What do I got to get rid of? I got to take away the 20. 32 minus 20. So what did I just figure out? The b value, which is the entrance fee, right? That's the thing that you get in to get in. So it costs $12 to get in. So now that I know, I already knew what the slope was. Now that I know what the y-intercept is, give me the equation. Y equals 4x plus 12. Now I'll do the second part of that in a second. I want you to see that this is the algebra way of doing it. We could have done a table. Which coordinate do I know in my table? Five. I know 5. How much does 5 rides cost? So this is number of rides. This is money. So 5 rides cost 32. What's the slope in this one? The rate of change? So it goes up by 4s, which means I could go backwards by 4s. So go backwards by 4s for me. 32 minus 4. 28. Before that, it was where? 24. And then before that? Then before that? 16. And before that? 12. And look. There's my flat rate. Which method is more efficient? The equation is, right? Even though the logic is good, you can go backwards 5 steps to get the flat rate that way. We know it's not always going to be like that. Okay. Now, this one said write the equation, but asks us to go further. It says now use this equation to determine the cost for 10 rides. Who's saying that? Is that Milo?
Yeah.
That's really good thinking.
See, he gets it.
I get it. I'm not saying it's right, but I get what you're saying. Okay, so for starters, that was a question I was going to ask afterwards. Okay, can I ask it afterwards and then it'll help you answer that question?
Sure.
Okay. No, I think you were right. It's just your logic was a little bit.
It was mismatched. It's in my
It was mishmashed, but I get what you were saying. Let's just finish this, okay? All right. This question sounds familiar because you actually did a worksheet on these things. Remember where you had to come up with an equation, then answer questions like, how much does it cost for 10 rides? Or 3 toppings on your pizza, or whatever. Okay. So in this case, it says use the equation to determine the cost for 10 rides. Is that an X or a Y? That's the X. So we've got my equation. So I'm going to go Y equals 4 times 10 plus your $12 to get in. Now the math, we've done these a number of times. 4 times 10 is 40 plus $12 to get in, total of $10 rides cost $52. I used the equation to get the information. Okay. Back to Milo's question. You see how the bit of information here said 5 rides. 5 rides cost $32. Can we not just double it if we're going 10 rides?
That's what I'm saying. except
You
you
said-
take away the flat rate.
Okay. Yes. You see, we can't just double what it was because 5 rides was $32. 10 rides would have been 64. Well, what's the problem with that? It's not 64. It's only.
The flat rate is normal.
That's right. You're doubling the flat rate as well. So you can't just double what's there. You can double part of it. And this is what Milo was trying to say. Which part gets doubled? Well, this part gets doubled, right? The amount you spent on rides. Because it's $20 for 5 rides. $40 is just, 10 rides is just $40. And then add your flat rate. Okay? So we can't just logically say it's double because you don't pay twice to get in. All right. Let's try another question.
I've never been.
Okay. Logan wraps presents at the mall at Christmas. He's paid 50 cents per gift that he wraps, plus a flat rate for showing up to work. One busy Saturday before Christmas, Dan wrapped a total of 80 presents, and he was paid $60. How much is his flat rate? So this is where the question starts to get a little bit more difficult. Our logic is a little bit harder. The numbers are a little bit different, but our algebra will always work. So we're going to use algebra to solve this. What is his rate of change? It goes up by how much every time? 50 cents. What point are we given? What information are we given? Not the y-intercept, but we do have a point. 80 and 60. You see how this is like, oops. This is kind of like time and money again. Except instead of calculating time in minutes, we're calculating time in number of presents. Every present goes along, you get money for that. So we know part of the equation already. What's the part of the equation we know? How much of the equation do I know so far? Y equals. Yeah, we need the equation first. 50 cents x plus the b we don't know. How am I going to figure out the b? You substitute, that's right. Before I do the algebra, I just want to do the table. Well, I just want to talk about what's wrong with doing the table?
If you're working with a decimal.
What's the problem with my table?
You got 80 presents.
I gotta go 80 times.
Why don't you do like?
I don't want to do 80 times, right?
Why don't you just do like 100 instead of 0.5?
Why don't we use the algebra? Because the algebra is way better than doing some other table. Okay? So the table is blah. Okay? The reason I'm teaching you algebra is so that we don't have to use the table. The table is inefficient and it's too crazy, especially for something like 80 presents. You don't want to count all the way to 80 and work backwards 80 times. Okay, the algebra will do this for us. All right. 0.50 times what? 80. And what's the Y value? 60. Help me out here. What's 0.5 times 80? 40? Which makes sense because 0.5 is half. So it's saying half of 80 is 40. Okay. What's my algebra tell me to do? Subtract the 40. He's getting $40 for the presents, but he got paid 60. That means there must have been a flat rate of 20. Okay, next. Use the equation to determine his pay for 40 presents. Okay. Y equals 0.50x plus 20. Is 40 presents the X or the Y? It's the X. What would it look like if I gave you the Y? What would I tell you? And you had to go backwards to figure out the X. Yes. Say he got paid, $60. How many presents did he wrap? That's when you would sub it in Y. But here we're going to substitute X. Okay. So Y equals 0.50 times 40 plus 20. What's 0.5 times 40? 0.5 times 40? 20. Plus 20. He gets paid $40 for 40 presents. $40 presents was half of 80 in his question. Could we just have divided his pay in half? We just say, well, 80, he gets $60. 40, he gets 30. Is that right? It's not. How come? It's the flat rate. Okay. If you took half of that, you would only be giving him half of his flat rate for showing up. And that's not fair. Okay.